In this video, we're going to discuss commutation relations between operators and their relationship to Heisenberg uncertainty. So we've already seen in this class that we use operators in quantum mechanics to measure physical observables. All the operators we use for this purpose are so-called Hermitian operators, which is a mathematical definition that has a few relevant properties that we care about. In particular, we've already seen first that Hermitian operators always have real eigenvalues. And because these eigenvalues correspond to the values of the observables that we obtain when we make a measurement, it's very important that they should be real quantities rather than imaginary or complex quantities, because they have to correspond to physical measurements, that is, things in the real world. Second, it turns out the eigenfunctions of these operators are orthogonal to one another, and then of course they can also be normalized. So together they satisfy orthonormality. This makes working with them relatively easy in many situations. Third, the eigenfunctions of these Hermitian operators form a complete set, which means that we can express any arbitrary state as a linear combination of the eigenstates of that operator. The fourth property, which we haven't discussed yet and we will now, has to do with the commutation relations between these operators. So in general, operators do not commute with one another. So what does commutation mean? In arithmetic, everything typically commutes. So for example, if I take the numbers 3 times 5 or 5 times 3, I get 15 either way. It doesn't matter which order I multiply them in. On the other hand, the same is not generally true for operators. If I act AB on f of x or BA on f of x, I will typically get a different result. In general, you should assume that two operators do not commute unless you specifically know otherwise, that those two operators are a special case where they do commute. To see how this comes about, let's take an example. Let's consider an operator A, which takes a function, differentiates it with respect to x. And we'll take another operator B, which multiplies that function by x. And then we can ask, do these two operators A and B commute? Well, to work this out, just like all the other work we did with operators earlier, we're going to act these operators on some dummy function f of x. We're not going to specify what that dummy function is, it's just going to be a placeholder that's going to help us make sure we get things like our product rules of differentiation correct and so on. So first I'm going to try acting AB on f of x. And so when I plug things in, that means I get d dx here for operator A, I get x here for operator B, and these are acting on f of x. So I multiply f of x by x, and then I differentiate it with respect to x. And in the end I do a product rule and I get f of x plus x times the derivative of f with respect to x. Now I'm going to do the opposite, where I act BA on f of x instead of AB. Plug in the definitions of the operator, so B is again multiplying by x, A is taking the derivative with respect to x, and we act these on f of x. So I first differentiate f and then multiply it by x, and I get this result. And so by comparing these two results, you can see clearly that we get a different result depending on whether we act operator A first or operator B first. When thinking about these sorts of commutations, it's useful to define something called the commutator for operators A and B. So the commutator is denoted by these square brackets and then two operators inside separated by a comma. And it's defined as just the difference between AB versus BA. If these two operators commute and the order in which we operate them on a function doesn't matter, then this commutator is going to equal 0. But if they do not commute, then we'll get a different result when we act AB on a function versus when we act BA on a function, and so we'll get a non-zero commutator. So this is just a very easy way of seeing whether or not two operators commute. We can take the example that we had on the previous slide and continue it here, just looking at it in terms of this commutator. So we can take this commutator AB, act it on that generic function f of x. So that means acting AB minus BA on f of x, or if we distribute this, it's AB on f of x minus BA on f of x. Now these two quantities in red and green are the ones we had from the previous slide that we worked out individually. So if you were to go back to that previous slide, you'd see that when AB acted on f of x, we got f of x plus x times df dx. And when BA acted on the function, then we got x times df dx. You can see that the second and third terms are identical, but with opposite sign, so they cancel, and we're left with f of x. So we get the commutator of a and b acting on f of x just gives us back f of x. Now, just like when we were doing the operator math earlier, the dummy function here is essentially uses a scaffold to help us figure out what the value of the commutator is. But once we're done with all our manipulations, we tear down the scaffold and see what the final result is. So in this case, this commutator a and b acting on f just gives us back f. So therefore, the commutator has the value 1, because if we acted on a function, it just gives back the same function. So this commutator has the effect of being an operator that takes a function and multiplies it by 1. The fact that this commutator is not 0 means that these two operators, a and b, do not commute. Let's do one more example with the position and momentum operators. So we're going to evaluate the commutator for the position operator, x equals x, and the momentum operator, minus ih bar ddx. Why don't you pause the video and give it a try and see if you can work out what the commutator for these two operators is. Hit play when you're ready to hear the solution. Alright, so just like before, we're going to start off looking at how xp acting on f and how px acting on f look. So in the first case, xp acting on f, these expressions are actually almost identical to the ones we did in the last example. The only difference is now we're multiplying the derivative by minus ih bar. So for xp, we get x times the p operator times f, multiply all that through, and we get minus h bar x df dx. Now we can take px acting on x acting on f of x, and we plug in the definitions of the operators. We get minus ih bar ddx times x times f of x. We multiply x times f of x, then we take the derivative of it. That gives us a product rule, and we get the result minus ih bar f of x minus ih bar x times df dx. Now we can evaluate the commutator, which is just the difference between these two results. So commutator of x and p acting on f is xp times f minus px times f, and plug in the values, minus ih bar x df dx minus, and then the value of the second commutator, which is here in the square brackets. Again, in this case, the first and third terms cancel, and we're left only with the second term, which amounts to ih bar f of x. Take away our dummy function now that we're done doing our manipulations, and we find that the position and momentum commutator is equal to ih bar. So this commutator takes a function and multiplies it by ih bar. The reason we care about these commutators is they are directly related to the ideas of Heisenberg uncertainty. In particular, you can derive a general expression for the uncertainty relationship between any two observables, a and b, based on the commutator of their operators. So in particular, this uncertainty in a squared times the uncertainty in b squared is greater than or equal to 1/4 the modulus squared of the expectation value of this commutator with some generic wave function psi. Now we'll come back and do an example of this later, but let's just now talk about it a little more abstractly first. So we're going to have two general cases. In the first case, a and b will commute, and if they commute, this commutator is 0. And then the integral of wave functions involving a 0 operator is going to be 0, right? We're going to be multiplying those wave functions by 0. So the integral will give 0, this whole right-hand side will be 0, and so we're going to get an uncertainty type expression that looks like the uncertainty in a squared times the uncertainty in b squared is greater than or equal to 0. In other words, there's no limit on the minimum amount of uncertainty we have to have. We can continue to refine our measurements as much as possible because this is just has to be greater than or equal to 0. So we can keep making the uncertainty in A and the uncertainty in B as small as we want. So if A and B operators commute, we can measure those corresponding properties simultaneously with as much accuracy as our experimental technique will allow us. On the other hand, if A and B do not commute, then we're going to have a non-zero value in here. We're going to get a non-zero value for this expression on the right-hand side, And so we'll get something like sigma a squared sigma b squared is greater than or equal to some non-zero value. And that means there will be an uncertainty relationship between those two observables corresponding to the operators a and b. And so that will give us an uncertainty principle. There will be some minimum uncertainty we always have to have in those two properties. And so if we end up knowing a better, we'll end up having to know less about b, or vice versa. To sort of understand how this comes about, let's look a little more closely. So there's a key fact that it turns out that if two operators commute, you can show that they have the same eigenfunctions. But typically they'll have different eigenvalues, but they'll have the same set of eigenfunctions. And so let's think about what happens when we measure. So let's say we're in some wave function capital psi, and we're going to measure that wave function for some observable using operator a. When we do that, that state capital psi probably isn't initially an eigenfunction of the operator a, but when we measure it, we force the wave function to collapse into one of the eigenfunctions of the operator a. We can call those eigenfunctions lowercase psi. And we're going to get back the associated value of the observable, that is the eigenvalue little a sub n corresponding to the particular eigenfunction psi sub n. So in other words, our big wave function capital psi, our initial wave function, can be viewed as a linear combination of the different possible eigenstates of a with different numerical coefficients c1, c2, c3. But once we measure it, we force the wave function to pick one of these possible outcomes, psi1, psi2, psi3. Maybe when we do it, it happens to collapse into psi2, as an example. And then, acting a on psi2 will give us back psi2 times the corresponding eigenvalue a2. So this, if it collapses into psi2, we would observe the value of this property corresponding to little a2. If we now go to measure a different observable with operator b, we have two possible cases. The first case, maybe a and b commute. And so the eigenfunction of a that we got up here, psi2, is also an eigenfunction or eigenstate of b. I should say I use eigenfunction and eigenstate interchangeably here. They mean the same thing in what I'm talking about. So because they have the same eigenfunctions or eigenstates, acting b on psi2 will give us back psi2 with whatever the associated eigenvalue for operator b is. So again, this eigenvalue b2 is probably different from a2 because it's a different property, but they have the same set of eigenstates. So if psi2 is an eigenstate for a, it's also an eigenstate for b. And this allows us to measure both properties a and b simultaneously. But if a and b do not commute, then things start to get interesting. Then we cannot measure both properties a and b simultaneously. To see how this works, let's just look a little more closely. Since a and b do not commute, that means they have different eigenfunctions or different eigenstates. So we can let lowercase psi be the eigenstates of operator a, and we can let phi be the eigenstates of operator b. And I put a little subscript n to differentiate the different possible states of psi, and I just picked a different letter k to represent the different possible eigenstates of operator b, just to help highlight the fact that these are different sets of functions, different sets of states. And of course, they each have their own sets of eigenvalues, a sub n and b sub k. So as we saw on the last slide, we started with some generic wave function capital psi. That was a superposition of many eigenstates of a. Then when we measure with a, we force that wave function to collapse into one particular eigenstate of a, say maybe psi2. Now we want to measure with b. Since psi2 is not an eigenstate of b, it's going to, when we measure with b, we're going to change the wave function and force it to collapse into one of the eigenstates of b, one of the phi k's. In other words, because psi2 is not an eigenstate of b, we can express psi2 as a superposition of the b eigenstates. So psi2 will look like some c1, phi1 plus c2, phi2 plus c3, phi3, etc. And I put little tildes over these coefficients here just to indicate and emphasize that these are different numerical coefficients than the ones we had on the previous slide with c1, c2. It's some other linear combination. But the point is, this eigenstate of a can be represented as a linear combination of the eigenstates of b. Now we measure with operator b, and it's going to force this wave function to collapse. It's going to collapse into one of these different states at random. Maybe it collapses into phi 3. And then we're going to get back the corresponding eigenvalue, B3, associated with our eigenvalue expression up there. But what's interesting is now we're in an eigenstate of operator B, and we are no longer in an eigenstate of property A. And so we've just actually lost information about property A. If we were to go back now, so we measured A, then we measured B, and if we try to measure A once again, we have to take this state we ended up in after measuring B, say phi 3, and we have to express it in terms of the eigenstates of A, psi 1, psi 2, psi 3, again with different numerical coefficients. This time I put primes on the coefficients, because again they have different values. And the point is it's some mixture of the different A states. And so if I measure A again, maybe it collapses back into psi 2 and I get back the same eigenvalue A2, but it might also collapse into psi 1 and give me the eigenvalue corresponding to state 1, or psi 3 and give me the eigenvalue corresponding to state 3, and so on. So the act of measuring a property changes the wave function and in general will destroy information we previously had. The only exception is if we do the measurement when we're already in the eigenstate of that operator. And because A and B have different eigenstates, whenever we measure one and then the other, we're going to be changing the state of the wave function upon each measurement, and each new measurement destroys information we had after the last measurement. And this is why uncertainty occurs. When we measure, say, position momentum, we measure position, then we measure momentum and destroy information we had about the position. Then we measure position again and we destroy information we just got about momentum, and so on. Now I have a whole separate video about measurement theory that tries to give a little bit more concrete of an example to help you understand this if you want to take a look at that. But finally, let's use the expressions we had from an earlier slide and derive an uncertainty expression for position and momentum. So we had this generic expression for uncertainty principles in terms of the commutator. So this can apply to any two operators, but now I want to take the commutator we derived for position and momentum and explicitly evaluate this expression. And so we saw previously that the commutator of x and position and momentum is IH bar. We're going to plug that in here and go ahead and simplify this expression. Now note, these vertical bars with a squared refer to the modulus squared, which is a way of squaring complex numbers that corresponds to psi star psi, or in this case z star z in my example. So we're going to take the whatever value we get from solving this integral, and we're going to take it times its complex conjugate to evaluate the square and then see what happens. The other thing I want to say before we get started is we want to derive these expressions in general without referring to any particular system. So we don't want to stick in particle in a box wave functions or any other specific wave functions. We want these psi's here to be very generic wave functions without any specific functional form. But we're still going to be able to simplify things. So let's go ahead and do this. We're going to set up this basic uncertainty principle for position momentum. We're going to replace this commutator of AB with a commutator for x and px. And then I'm going to plug in the value for that commutator, IH bar, right here, and start simplifying. Now IH bar are constants. This whole thing, psi, IH bar psi, is an integral. I can pull the IH bar outside the integral, and I'm left just then with the integral of psi star psi, psi with itself. And that integral is just a normalization integral, and we know that we can always normalize our wave function. So this integral of psi with itself is equal to 1. So if we use that simplification, then we just get this uncertainty in x squared times the uncertainty in p squared is greater than or equal to 1/4 times the modulus squared of IH bar. Let's take that modulus square, which is basically just IH bar, times its complex conjugate, which is minus IH bar. And then of course bring along the 1/4 for the ride, multiply this all out, and I get minus I squared H bar squared over 4. I squared is equal to -1, which cancels the negative sign in front. So we get that sigma x squared, sigma p squared is greater than or equal to H bar squared over 4. take the square root of both sides, and we get the uncertainty in x times the uncertainty in momentum is greater than or equal to h bar over 2, which is just the Heisenberg uncertainty expression we had before.